Hi, my name is Andrew Wang, and this is my Physics 2211 Lab 3 report. In this lab, there are two parts. For part 1, the purpose was to use coding to simulate a black hole to find its mass. For part 2, the purpose was to use the black hole mass found in part 1 to find the initial velocity needed for a spaceship launching off a planet to get close to a black hole but not touch it. The fundamental principle this lab demonstrates is Newton's second law of motion via the momentum principle, the position and velocity update formulas, and the universal gravitational force. For part 1, the system was the star and the black hole. For part 2, the system was the spaceship and the black hole, and the surroundings are everything else in this universe besides the system. For my part 1 code, I set the star mass to 2e30 kilograms and the change in time to 24 times 60 times 60 seconds, the number of seconds in a year. Using the star's mass and the initial and final velocities of the star, I was able to find the change in momentum over the change in time, which is equal to the net force applied on the star by the black hole. F net parallel would be the change in momentum magnitude over change in time times p hat. Using this, F perpendicular would be F net minus F net parallel. Knowing each component of F net allowed me to create arrows visualizing the simulation better. To find the mass of the black hole, I multiplied the magnitude of F net by the magnitude of the distance between the star and the black hole squared divided by the g constant times mass of the star. This comes from the universal gravitational force formula. The mass of the black hole I found through this was about 1.42 e34 kilograms. For my part 2 code, I set the black hole mass to what I found in part 1. To calculate the net force on the planet, I added up the force the ship applied on the planet and the force the black hole applied on the planet, using the gravitational force formulas to find each of them. To find the net force on the ship, I added up the force the black hole applied on the ship and the force the planet applied on the ship, using the gravitational force formula to find each of them as well. Knowing these forces, I was able to use the velocity and position update formulas to find the new position of the planet and the ship at each change in time. I kept on trying new initial velocities for the ship until there wasn't a time where the ship would either get sucked into the black hole or hit the planet. Eventually, an initial velocity for the ship I found to pass the black hole was negative 2e7 meters per second in the x direction and 1e7 meters per second in the y direction. A possible source of error may come from the fact that every change in time, the black hole mass calculated will be slightly different. Even if an average of these numbers is used, it's possible that the black hole mass is not entirely accurate. And is at best an approximation. Though related, the net force and its parallel and perpendicular components and the rate of change in momentum and its parallel and perpendicular components are two different concepts. While the net force and its parallel and perpendicular components are related to the motion of an object, the rate of change in momentum and its parallel and perpendicular components are related to the mass and velocity of the object. This means that changes in mass or velocity will affect the rate of change in momentum, but not necessarily the net force acting on the object. This meant that we can calculate change in momentum based on the data, and we can only deduce the net force based on the rate of change of the momentum. To get the spaceship to enter the orbit around the black hole, you will need an initial velocity that is lower than the current one, but not too much lower where the ship would get sucked in. I was unable to pin a specific initial velocity for this though. Thank you for watching.